All right, let's dive into this explainer with what honestly sounds like an impossible premise. Define gravity to soar through the sky, only to come hurtling back down and intentionally crash land into the sea, and somehow do it safely. We're exploring the fascinating intersection of aerodynamics and hydrodynamics, which is this highly specialized field of engineering that basically defies the odds. It combines two entirely different disciplines to create machines capable of conquering multiple environments.
Just think about the sheer physical stakes here for a second. Building an aircraft that can safely navigate the skies is incredibly difficult on its own, right? You're constantly fighting for aerodynamic lightness. Every ounce matters. But then, on the flip side, building a seaworthy vessel that can handle the unpredictable, crushing nature of water requires extreme hydrodynamic durability. So, making a single machine that does both? That is an absolute engineering marvel. You're basically asking one vehicle to obey two completely different, fundamentally opposed sets of physical laws. So here's our roadmap to unpack all of this. First, two worlds, one machine. Second, decoding water aircraft types. Third, the amphibious advantage. Fourth, unique engineering challenges. And finally, number 5, the future of water flight.
Let's start with Section 1. Two worlds, one machine. The core friction of water aviation. This right here is the ultimate boundary. As our sources point out, combining traditional aircraft engineering with specialized marine design creates a fascinating paradox. Think about it. Aerospace engineers will literally fight tooth and nail for every single ounce of weight reduction just to get a machine off the ground. They want everything incredibly thin, light, and perfectly streamlined. Naval architects, on the other hand, well, they need everything to be thick, heavy, and extremely buoyant to survive the relentless battering impact of crashing waves. Creating an aircraft capable of operating safely between these two elements means you can't just be an aerospace engineer. You kind of have to be a naval architect at the exact same time, carefully balancing that delicate weight against necessary brute strength. Moving on to Section 2, decoding water aircraft types. Meet the fleet. Now, at first glance, you might think all water planes are essentially the exact same thing, but we're actually looking at 4 distinct species of water aircraft here. Each one utilizes totally different engineering solutions to operate safely on the water, and of course, each comes with its own unique set of advantages and limitations. We've got the floatplane, the flying boat, the amphibious aircraft, and the hull aircraft. Let's contrast the unique trade-offs of the two most recognizable types, just to see how this plays out in the real world. On one side, we have floatplanes. These are your conventional aircraft, but they're fitted with external pontoons mounted beneath the fuselage. Because the main aircraft structure remains safely up above the waterline, they prioritize a lighter main body. But there's a massive penalty here. Those big external floats create an enormous amount of aerodynamic drag, which drastically reduces flight efficiency. On the flip side, we have flying boats. These offer a much more elegant solution for scaling up. With these, the fuselage itself actually forms a boat-shaped hull that sits directly in the water. This optimizes the aircraft for much larger structures and completely eliminates the drag of those external pontoons. And internally, the engineering realities of these two approaches are completely different. Floatplanes rely on individual buoyancy chambers built directly into their external pontoons to keep the whole main aircraft afloat and balanced. Flying boats, conversely, feature these deep, watertight compartments integrated directly into the belly of the hull itself. Plus, the flying boat relies entirely on the precise hydrodynamics of that specific hull shape for stability and spray deflection, while the floatplane frequently has to rely on stabilizing wing floats just to keep from tipping over in rough chop. Let's jump to Section 3, the amphibious advantage, the ultimate flex. You see, the true magic of amphibious capability isn't just about floating. It's a supreme operational flex. By definition, amphibious capability means the aircraft can operate from both water and conventional paved runways. And it pulls this off using heavy-duty retractable landing gear systems. So actually, both floatplanes and flying boats can be amphibious. It simply means they possess the complex hardware required to bridge that gap and transition seamlessly between the land and the sea. Just imagine a single flight that begins by taking off from a scorching, cracked concrete runway, transitions seamlessly over a jagged, rocky coastline, and ends with a remarkably smooth touchdown right on the open water. With heavy-duty retractable landing gear tucked securely away into sealed side pods and highly versatile cabin configurations, this one single machine seamlessly conquers completely different environments in a matter of hours. This gives operators absolutely unmatched flexibility. Because of amphibious engineering, an aircraft can move fluidly between traditional airports, highly remote lakes, winding inland rivers, busy urban harbors, and sprawling coastal regions. And they do all of this, crucially, without requiring specialized multi-million-dollar infrastructure at every single destination. And this operational flexibility serves vital, real-world applications. We're talking about aerial firefighting, where an amphibious plane can literally skim a lake to scoop thousands of gallons of water in a matter of seconds. We're talking about deep Arctic logistics, dropping critical supplies onto an unmapped, freezing lake where no runway could ever realistically be built. From specialized military operations and emergency medical evacuations to remote bush flying that connects isolated island communities to the rest of the globe, this capability isn't just cool, it's an absolute lifeline.
All right, Section 4, Unique Engineering Challenges, the Crucible.
Designers are basically fighting a relentless forefront war when building these machines. First, for water handling, they have to calculate exact buoyancy and hull shape, mainly because water is roughly 800 times denser than air. Hitting water at high speeds with a poorly designed hull can literally tear an aircraft completely apart. Second, they fight environmental stress, combating constant, aggressive corrosion from salt water and the physical battering of wave impacts. Third, for aircraft balance, exact weight distribution and unusually high engine placement are absolutely critical just to keep the propellers spinning safely above all that chaotic water spray. And fourth, they are constantly weighing hydrodynamic necessity against aerodynamic drag. It is a high-stakes balancing act of physics, for sure. And remember, unlike a static concrete runway that just sits perfectly still, water is highly dynamic. When an amphibious aircraft comes in for a landing, the pilot is immediately wrestling a multi-ton machine against changing currents, relentless waves, shifting winds, unpredictable surging tides, and even local marine traffic. Stabilizing a fast-moving aircraft in those volatile conditions requires absolute precision. If the hydrodynamics aren't perfectly dialed in, the water will win, every single time. Which brings us to our final section, number 5, the future of water flight, sustainable horizons. So what does tomorrow look like? Well, tomorrow's tech aims to solve these age-old hydrodynamic challenges with some truly incredible innovations. We're looking at a major shift towards sustainable propulsion through highly efficient electric power, supported entirely by renewable energy ecosystems and smart seaplane terminals. We're seeing radically advanced hull designs utilizing ultra-lightweight composite materials alongside fully connected amphibious fleets using AI-assisted flight systems and autonomous navigation. It's a vision of water aviation that is cleaner, much smarter, and completely interconnected. But I want to leave you with this final thought to ponder. Despite all of this evolving technology, the AI flight management, the sleek electric propulsion, the advanced lightweight materials, can we ever truly conquer the fundamental boundary between air and water? Because at the end of the day, water remains water and air remains air. The core engineering challenge of operating safely between two entirely different physical environments is exactly the same today as it was a century ago. No matter how advanced our tech becomes, mastering the sky and the sea in a single machine will always remain a thrilling testament to human ingenuity, constantly pushing the boundaries of nature.